See, listen here. Okay. We have already discussed certain types of codes. You know BCD code. Then you know 2421 code. I discussed that also. And XS3. These three were self-complementing codes. And finally, we had gray code, which is a self-reflecting code. Right. Okay. So now we'll discuss about, see, now we know that when we have an analog signal, a naturally occurring signal, we convert it into digital form. Now, after conversion to digital form, we can either store it, or we can process it, make some changes to that, or we can transmit it. Right? It is possible for me to transmit. Now, suppose if I take the case that I have some data, so I am the sender and I'm sending it to somebody. I call it the receiver. So when I transmit this data, whatever I have, now this channel through which I transmit it, it can be air. So that is called the communication channel. Okay. So this medium, when I'm transmitting it, it is possible that my data can, some of the bits in my data can get interchanged. A one can become a zero, or a zero can become a one. Okay. So that is because of some noise in the channel. That is unavoidable. So you will always have noise. So that means now I'm sending some data to my receiver. How does the receiver know that what they have received is exactly what I transmitted? Right. I need to ensure that what has been transmitted is the same. I mean, they have to, there should be some kind of a communication between the sender and the receiver. So which tells them that, okay, I'm transmitting a 4-bit data or a 12-bit data. Okay. And so now how do they check? For checking whether the what they have received is correct or not, we use something called error detecting or error correcting codes. Okay. So one of those kind of codes is called a parity code. Parity bit we add. So that means if I have my data like this, I can add one more bit. It could be a 0 or it could be a 1. So, and this totally, that is my data plus my parity is what I transmit. Okay, I transmit it. So data plus parity is transmitted. So at the receiver end, they will check whether this parity, I mean, it is satisfying the condition. So there will be a circuit there also, which checks for whether it is correct or not. So it checks the data. So here at the sender end, I add some error detection code there. I add it to my data, and at the receiver end, I will check. Okay. So, so parity checker is a code. Parity bit is a code that I can add for error correction and detection. Okay. Now, suppose if my data is 000. Okay. Now, what can it change to? If I have a 1-bit change that happens, suppose it can become 001, or it could be 010, or it could be 100. Okay, so there are multiple options that are available that my bit could, if a single bit error I'm looking at. Okay, now we will focus on only single bit errors. Okay, single bit error, how to detect it. So now let's look at, okay, so now I'm talking about something called an even parity generator. So let me write my data. Okay, my data is going to be I will explain this in 3 bits. That will make it easier. Now, an even parity generator is a circuit wherein uh, it counts the number of ones in your data. Okay, how many ones are there in your data, and it tries to make the total number of ones even. So, even parity generator tries to make the total number of ones even. Okay. Now 000. How many ones do I have? No ones. That means one is the number of ones is zero. Zero is an even number. That means I don't add anything. I keep the parity as zero. Next case, the second line I have my data is 001. I have a single one there. So the number of ones is odd, right? The number of ones in my data, and this is my data. The number of ones is odd. So I have to make it even. If I have to make it even means I need to add one more. So that means my parity is going to be 1 in this case. So then I look at the total number of ones. Now I will look for the, after adding parity, if you see, now the number of ones is 1, 1, 2, which is even. Got it? The purpose of my even parity is to make the total number of ones in that code even. Second case, this one. What about this case? 1. So I have to add 1. Now, this one, I have 2 ones. So I don't have to make it even. It's already even. So I add a 0 there. Next one, it is only single one. So I add it. All right. So the purpose is just to make the number of ones even. So can I draw a circuit for this now? Let's look at these things. Where all do I have my output 1? I have my output 1, P is 1, whenever the number of ones, this here number of 1 is, this is odd, right? Odd number of ones. Then here again it's odd. Here also it's odd. Here also odd. So whenever the number of ones in the circuit is odd, only in those cases my output P is 1. So which kind of a gate? XOR. XOR gate will give me that kind of an output. So I can generate my P even parity bit using okay. Is that clear? Yes. You can connect, but we always go for standard circuit with 2 input gates. Okay. So so here we have, so this is how my parity is generated. So this happens where at the sender end. Okay. Sender has created the even parity generator. Okay. Now, when the sender and the receiver, they communicate with each other, I told you earlier itself. So they follow a certain set of rules for communication. We call them as protocols. Okay. So in that, it would be known to the receiver that how many bits of data is being transmitted, what kind of parity have I added. I can also add odd parity. Okay, odd parity means just the opposite. It will try to make the total number of ones odd. Okay, so that kind of a circuit also you can have. So so that communication or that information is also communicated to the receiver about the number of bits of data that you're transmitting plus the kind of parity checker circuit that you have added. Okay, parity generator that you have added. So, and then now let's look at what happens at the receiver end. Okay, so there now after this data is what is being transmitted, the data that is being transmitted is going to be 0000. That means this much is transmitted, right? 4 bits. I had only 3 bits of data. The parity bit is appended to that or attached to that, and we send that. So we will have 4 bits being transmitted. Got it? Now, at the receiver end, now I have to check whether this from this 4 bits I have to figure out whether it is correct or wrong. Okay. So at the receiver and what I will do, I have what comes in is like I have a parity checker circuit there. Okay, parity checker. Now the purpose of this parity checker is to tell that yes, there is an error. There is some error. Only the error cases I want to detect. Right. If it is correct, I don't have a problem. That is the correct data. So for that purpose, now I am going to say that my data is D2, D1, D0, P as I transmit it. So I have now it's a 4-bit combination that comes in. Now this checker circuit, it will generate a false case or it will produce an output 1 if there is an error. So checker will give output gives output 1 if there is if error is present. Okay. So all the true cases, the output is going to be 0 and only if there is an error, output will be 1. Okay, for the circuit. So now if you see, here also it is, what is it going to do? The checker is going to count the total number of ones and see if it is even. Because it is an even parity, the number should be even, right? So 0, 0, 0, 0, there's no problem. Because if you see in that, the total number of ones is 0, which is an even number. So the output is true. Now, what about this? Now the total number of ones is odd, which is wrong, right? I want the total number of ones. If I have transmitted it using parity, I have converted it into even and transmitted. But I am getting here the total number of ones as odd. So I understand there is a problem there. Okay. Next case also, I'm getting odd. So wherever odd number of ones come, I have an error there. And the output will be 1 in that case, the checker output. Okay. All right. So is that clear? There's no confusion, I hope. Okay. So just check for the number of ones. If it is even, since we have used even parity, it is correct. So the output will be 0. If the number of ones turns out to be odd, then there is an error. The output will be 1. Now, what kind of a circuit can I represent this using? XOR again. People have become very smart. So only when there are odd number of ones, we will get an output 1, right? So that is the case of an XOR gate. So directly I can represent it using XOR. So I go for 2 XOR gates. I mean 3 XOR gates basically. D2, D1, and D0. Okay. All right. So it is actually my C is equal to D2 XOR D1 XOR D0 XOR P. All right. Okay. Now, so it's clear. Have you written down? Okay. So same way for the previous one also, you should have written the formula. I didn't write the formula here. You can write what P is equal to. Is equal to D2 XOR D1 XOR D0. Okay. So always for any design that you have to write the switching expression by which you are representing the circuit, right? You get the switching expression, then I draw it using gates. So, no. Now I have a problem using parity. Parity looks very nice and all that. It cannot detect all errors. Suppose if I said that single bit error detection is possible. Okay. Now suppose if I have a case where 00011. Okay, this P is my parity. Okay. Now 00111. If it is transmitted like this one has changed. Yes, I can detect it. Single bit error, one error is okay. Now, if I have 00 uh, 111, okay, same thing, 00000. Here it becomes 01111. Okay, so the parity is also, how many bits I have here? 1 2 3 4 5. So 1 2 3 4 5. Okay, so 1 2 3. Okay, I have added one more. Wait, let me do that. Okay, so I change it to 01111. Now see what happens here. Two bits have changed. Okay, this is my parity bit. Okay. Okay. No. See, this is here. It is 000. This is the original one. Okay, this is the original message. Like this. This is both are the original ones. Okay, I'm not changing the original one, but I transmitted it during transmission. Two of my bits have changed. But my parity, is it correct? It is correct, no, because I have total number of ones have become even. That means if I have two errors, it will not get detected. Now if I have three, so that means 11111. In this case, it will get detected because the total number of ones is odd here. That means the parity has some problem. We will understand. So that means odd number of errors can be detected by using this parity. Okay, parity check. Either odd or even. It depends on which type of parity used. But for even parity checker, you can detect either one error or three errors or five errors and so on. Okay. So we have that limitation when we are using parity. So there are various other error checking codes. We are not going to study all that. Now we just covered some codes related to. I wanted to let you know about a code which is used for error detection also because that is important in communication. Okay. So now let's start with combinational circuits, which I started sometime and then left. So now see, when I want to design any kind of a digital circuit, I call that process as logic design. Designing of any digital circuit is called logic design. So if I want to analyze a circuit, I have to derive a switching expression that represents the behavior of that circuit, right? Every circuit that we had, we always got a switching expression from which we drew the schematic. Okay, so we should have a switching expression to analyze the behavior of a circuit. Now we have two types of circuits. One is a combinational circuit, wherein all that you have done till date are combinational circuits, wherein we give inputs and depending on our input combinations, we get a specific output. Okay. Then I also mentioned earlier, we have something called, so this is combinational circuit, where output depends on present input. Then we also have something called sequential circuits, wherein the output depends on, we have a memory element involved in sequential circuits. I had given an example of a traffic light system. So that is like if the light is yellow, whether it goes from yellow to red or yellow to green depends on what was the previous state, right? If it was green previously, then from yellow we will go to red. So same way, if you have an elevator system, how does it travel? All that depends on memory. Who all have requested for the lift? So there, those are such kind of systems wherein we have memory involved. Okay. So your output is not just going to depend on what input is given. It will also depend on some previous output which is stored in memory. So a memory element is involved. So this we will study in detail later. After your mid semester, we will come to sequential circuits. So at for the present, our focus is on combinational circuits, and the simplest or the most prevalent used combinational circuits are arithmetic circuits. So arithmetic circuits, we have adders, we have subtractors, maybe we can have multipliers, so on. We can have any type of circuit. So we will start with the basic arithmetic circuit, which is adder. All right. Now, when I say about a half adder, I have two kinds of adder. I have a half, when I talk about adders, I have half adders and full adders. Now, suppose if I want to add two 4-bit numbers. So when I add these two, I start from, this is my LSB. So when I start adding these two, my output is going to be A0 plus B0 gives me S0. Now there can be a carry which is generated by this, so I call it C0. It's possible to have a carry. You might have a carry or not have a carry, and then you get. When I add all these three, I get S1. Again, if a carry comes in, I get this becomes C1, and then I get S2. And if I have a carry, which is C2, I get S3. And I also have another carry, C3, which is my final carry, C out as you say. So my result is going to be 5-bit long. Is it not? My result will be 5-bit long if I'm adding 4-digit or 4-bit numbers, if I'm adding 4-bit numbers. Now, a half adder is a circuit which can add only 2 bits. So I can add A0 and B0, but I cannot add a carry with it. Okay, so 2 bits. So if I have this, you might be thorough with this truth table by now. This is the example we go to all the time. So when I add these 2 bits, the sum is 0, there is no carry. When I add 0 and 1, sum is 1, no carry. 1 and 0, sum is 1, no carry. 1 and 1, I get sum 0, carry 1. Because 1, 0 is the output. When I add 1 and 1, my output is 2, which is 1, 0. So this is a carry. Now, if I want to draw this circuit, okay, or I write the formula for the circuit or the expression for the circuit, I get A bar B plus AB bar. Okay. Carry is true in this case alone. So carry is AB. Okay. Now let me draw the circuit. If I draw the circuit, I have A. I take the complement. I have B also. Okay. This is just for the sum. Okay, let me draw for the sum. Now, if you see here, my signal A, okay, if the signal A input, that A input has to reach my sum, output S, how many stages does it have to, or how many gates does it have to pass through? This is one gate. Okay, this is one path that it can take. It goes like this, right? This way it can come. That means it passes through a NOT gate. I'm talking about input A. Okay, input A passes through this NOT gate, then this AND gate, and this OR gate to reach sum. That is one path. This is path one. Or there is one more path which is possible for A. See where A is connected to? A is connected to this gate, right? So A can either go through that path or this path to reach sum. Yes or no? Two ways in which the input that you give can propagate to the output. There are two ways. So this is path 2. Now in path 1, how many gates are coming in the path? I have 3 gates, right? Not, and or. So I have 3 gates there. And in this lower path, path 2, I have 2 gates only coming in that path. Okay. Now That means each gate, it's, see, every gate has a small amount of delay associated with it. It's not like I give the input immediately I get an output. Delay will be very very small, but there is a delay for every gate. That means if I have to traverse or go through a path which has more number of gates, I will have more delay. Okay, delay to reach the output. Okay, so now I'm saying that all the gates have uniform delay. The delay associated with each gate is delta. Is delta. Okay. So there is a delta delay here, delta here, delta here. So I get a total delay of 3 delta here. And in this path, if A is going, I will get a delay of 2 delta. All right. Is that clear? Every gate has a small amount of delay. So when I add up that delay, I will get the total delay of the path. So this is referred to as propagation delay. So it is the delay for a signal from the input to propagate to the output. Okay. So the delay involved in propagating a signal from the input to the output of the circuit is called as propagation delay. Okay. Now, this is a very important uh, parameter because we always want to design circuits which are fast, right? I want to get my outputs as fast as possible. So, I will try to keep my propagation delay as less. Okay, so for that is why we try to minimize circuits, come up with the optimized solution, because the more the number of gates you try to introduce into your circuit, the delay is going to be larger. Okay. So, and so always a signal has multiple paths to traverse to reach the output. As I showed you, path one and path two is possible. So, uh, so the delay is not the same along all the paths. Okay, delay varies according to the path chosen. Is it clear? The concept of delay is clear. So, yeah, so that means that I just showed my what I showed was my circuit implementation for sum using uh, A XOR B, no, A bar B plus AB bar. Instead of this, I know that this is equal to A XOR B, right? If I represent the circuit using that, it becomes, this is carry, right? So I could have eliminated the need for all those gates, those additional gates, if I use an XOR gate. Yes or no? Yes. So now, but we have a problem when we use a half adder. That is, half adder I can use only for adding my LSB bits, right? If I'm adding A0 and B0, yes, I can use a half adder because I understand that there might not be a carry. In the initial stage, I don't have a carry. The LSB, when I'm adding, I only have the 2 bits to add. But I cannot use it for any further addition because for any further addition, I have to have the carry from the previous addition, right? Previous bit addition, I need to add that also if I have to get S1, S2, or S3. So that means this is an impractical solution to be used as an adder, half adder, basically. Okay, I can only use it for LSB addition. So we will look into a full adder. So now what is a full adder circuit? Full adder circuit has 3 inputs. So first it takes the input, so 1 bit of A, 1 bit of B, and 1 carry bit from previous addition, previous bit addition. All right. So there are 3 inputs for a full adder. Okay. Okay. Now, if I am going to represent the circuit, it's going to be something like this. If I have a 1 bit full adder, Right. So if I add bits A0 and B0, I get the sum S0 and I get the carry C0, and I have an additional carry which comes from the previous bit. That is why I call it C minus 1. Okay. If I generalize this, okay, I will draw a 4-bit cascaded form. Then right. Yes. Single, no. S0 means if I have a carry generated, it goes to the next one as C0. Hmm. हाँ S है. This is the S. Output, there is a sum and a carry. Okay, each one has a sum and a carry. That is what I'm drawing. No, this is these two are the outputs from the first block. Is it not? The arrow is outside, going outwards. That means S0 and C0, the outputs of the first block. FA0. Then FA1 has outputs S1 and C1. But this carry has to be passed on to the next bit because I need to add quiet. Okay, this carry has to be added on to the passed on to the next bit. Got it? So this is what it looks like. And if I generalize and draw, saying AI, BI, I have my output SI, CI, and this carry will be C, I minus 1. Right? The previous carry. Okay. So in every addition, we will have 3 bits, one carry which comes from the previous addition. Okay. Now let's write the truth table for this one. Are you done with drawing? Those who are drawing and all? So, so if I have A, B, and C in, I call it C in now. Okay. So in the first 3 cases, we do not have a carry. The fourth case, when I add 1 plus 1, I get 1, 0 as my answer. That means 0 is in the sum and 1 becomes my carry. Next case, again, addition, no carry. This 2 again, carry is there. 1 plus 1 gives me a carry and the sum is 0. Again, I get a carry, sum is 0. 1 plus 1 plus 1 is 3, which is 1, 1. So I have sum bit as 1 and my carry bit as 1. Okay. So what is sum going to be? Sum is going to, yes, you people are ready with answers. So sum is 1 in the cases where the number of ones in my input combination is odd. Okay. Either when I have one single one or I have three ones. So I can say this is a XOR gate and I can write A XOR B XOR C in. Now carry. Okay. Carry, let me write down the expressions for carry also. The carry, these are the four expressions. Carry would be, the first case is A complement B C in plus, here I have A B complement C in. What B plus C? Why? I'm writing the min terms, no, now. I'm writing min term expression, no? Okay. So let me simplify. I'm writing expression, then I want to simplify. So then I get A B C in bar plus A B C. Okay. Now if I'm going to try to simplify this, in the first two, I can see that C in is common. So I will write C in A bar B plus A B bar. Similarly, in the next, the next one, what do I have? There should have been one more C bar. No? C in bar. This was C in bar. Sorry, I can. That is what there was on top. See, people are not telling me when I write wrong. A B C in, then A B C in bar. This is again C in bar and A B C. Okay, so let me combine the terms which have C in. Which one? Second term is A B bar C bar, no? Oh, this is the one. Okay, fine, fine. Okay, A B bar C. Then the third one, A B C in bar. Now it's correct. So we have only one case where C in is. There's only one case where C in is. Okay, fine. Okay, now let's go to. Okay, so let's take the case where C in is one A B bar and A B. Plus A B. Okay, I combine the first two terms and I combine the last two terms. Okay, I'm getting like this. So what is this? This is A XOR B C in plus C in bar plus C in will be 1. So that means this is one way to represent my carry. Okay, this is my carry expression. Any doubts? Okay. Now, similarly, instead of this, suppose if I go to, I decide, okay, I'm going to draw the truth table. Okay. So if I'm going to draw the truth table and find the value for carry, yeah, I mean K map and fine. So I have, so I have the carry 101. Okay. I get like this. Okay, so now I will group them. This is one group. So I say C is equal to, in this case, the row is changing, column is the same, that is BC in. Second group, row is the same, so I have A And what is not changing? 0, 1, 1, 1. C in is not changing. C in is 1, so I leave it like that. And the last group that I have, again, A, row is the same, so A, and 1, 1, 1, 0. B is not changing and it stays as 1. So C can also be written as BC in plus AC in plus AB. Okay, this is another representation for carry. Okay, so now we have two representations for carry. Now this representation that we have here, carry is equal to, this is very useful to us in some concepts that we will discuss further. Okay, so carry can be represented in either of the way. Okay, any of the circuit is fine for carry. Yes. Which one? Carry will become. Okay. That is okay because we have minimized it. This is not minimized form. As you can see, the one we have on top is not the minimized form, right? Here, this is a minimized form. There are two representations possible. Don't look for the minimized representation now. What I'm trying to tell you is that we can represent it in two ways. And why we represent carry this way is what I will discuss. Okay, why we are representing it. Is this much how we got the carry? Is that clear? Now, why we use that carry, this carry, we will see. Okay. So now, see now if I'm going to represent a full adder using half adders. Okay, I'm trying to represent a full adder using half adders. Quiet. What is the discussion there? I've told you earlier also. Those who want to talk, go outside. Okay. So now in a half adder, you know that I can add only 2 bits. So if I can add A and B as my inputs, I have a carry and a sum as the output of a half adder. Okay, this is my half adder one. So sum will be what? What is the expression for sum? A XOR B. If you don't remember, look back. Okay, and C will be AB, right? Now, if I have another half adder, this is another half adder. Now, this is one of my inputs, A XOR B, which has come out as a sum. I take it as one of the inputs, and I have my C in as the other input. So, what will be the sum generated? It's going to be the XOR of the two inputs, is it not? So it is going to be one input is A XOR B, that XOR with the second input C. So now have I got the expression for the sum of a normal full adder? What was the expression for sum? Sum I wrote no here. A XOR B XOR C in. Now using two half adders, I have been able to get the sum. Yes or no? Yeah. So now let's see. Now we need to get the carry. Now what will be the carry of this? Carry is going to be the first input and the second input. You see the first half adder, it is A and B, which is the carry. Same way here, my first input is A XOR B. So A XOR B and C in, right? This is my carry. Okay. Now, if I give these two carries to an OR gate, do I get the carry of a full adder? If you go back to the previous page, I have written that carry is equal to A XOR B dot C in plus AB. So this can be satisfied, right? Is it not? Because A XOR B C in, what are the two inputs? A XOR B C in plus or AB. So I generated the carry and the sum of full adder using two blocks of half adder circuit. Yes or no? Okay. Okay, each stage you just need to know the expression for sum and carry of a full adder, of a general full adder. Sorry, half adder, and then you see what the outputs you're getting accordingly. Okay, so I need to add 3 bits. I cannot add 3 bits using a half adder. So I have a second half adder which helps to add the third bit also. So for carry, I need to do some adjustments. So I need an additional OR gate. Okay. So I'm able to get it in the form. Okay, I'm able to get it in this form. Okay, this form given. So now this kind of an adder circuit that we have, okay, wherein the carry from a previous stage is used to add the bits in the next stage, we call it a ripple carry adder. It's also called a ripple carry adder. That's because the carry ripples through. Okay, from the first stage it moves to the second stage, then from the second one what is generated moves to the third stage and so on. So it's called a ripple carry adder. Now, if you look at this circuit, you can understand that I have so many carries generated. I have C0, C1, C2. But do I need these things? Actually, what is that I'm interested in? I am interested only in this particular carry, right? My C3 is the actual carry of the addition of 4 bits. So C3 and these sum bits, S0 to S3 is what I'm interested in. So now I have to wait. So suppose if this first adder circuit has a delayed delta. So this comes here. So if I have a 6, so here I have a delay of 4 delta before my final carry is generated. Yeah. But suppose if I have a 16-bit adder, what happens? How much of delay? If I'm saying it's a single, I will have 16 delta delay, right? So that means the delay to compute my sum. Sum is not complete without the carry. I should have the MSB also, right? So the time to compute my result is proportional to the number of gates I have. Excuse me, I'll just come in. Okay. So I will have a total delay of, so the delay will be proportional to the number of bits I need to add. If I have to add 16 bits, I will have 16 units of delay. If I have to add 32 bits, that many units of delay, provided that each unit I'm talking about has a delay of delta. Okay. Single delay I'm saying. So that means, now, can I do away with this? Can I make my circuit faster? Okay, that is my, because I don't need these intermediate carries. I am not interested in the intermediate carries. Can I have a mechanism by which I can pre-compute or predict these intermediate carries beforehand? Okay, can I calculate it so that I can make my process of addition faster? That is what I am looking at. So now if I have to have something like that, if I'm able to predict or pre-compute the carry beforehand, that means I will have to have additional logic. Is it not? I should have some circuit for that. So I will have extra logic, extra hardware. That means more gates are put in. And if I have more gates, that means on my design, whatever, more space is taken up. So the more the space that your design takes up, more costly it becomes to manufacture it. So the cost will go up. Okay, so cost is going to be higher. Cost will increase. But doing this, if I'm able to speed up my circuit, I want my circuit to work faster. If I'm able to achieve speed, then I'm okay with adding this. Okay, I can have a kind of a trade-off. It's called a trade-off. That is, if I reduce my delay, my cost goes up because I have additional hardware. So I'm doing something to make my circuit faster, but that is at the expense of cost or something else. Maybe more circuit, more number of gates means more power is consumed, more heat is dissipated, and so on. So many things come in. But if our main aim or objective is to make our circuit faster, we are ready to have these kind of shortfalls on the other side. So that is called a trade-off. Okay. Usually in any kind of design that we come up with, you will see that there will be some amount of trade-off. It's not possible to keep everything balanced. Okay, some things will go up, some things will come down. So there is a trade-off. Okay, now, so it is possible to do something like this, and that is called, we do it through a carry look ahead adder. Okay, called CLA. Okay. Now, also one more thing. Now we discussed 1-bit full adder. Actually, 1-bit, instead of 1-bit, we get 4-bit adders as a block, as a ready-made circuit in the market. Okay, this is not related to carry look ahead adder. I had to mention this also related to the full adder circuit that we learned. It is, we get these 4-bit adders or 8-bit adders as blocks or slices in the market. Okay, so they're ready-made circuits, and I just need to cascade them to make a 32-bit or 62-bit adder. Okay, so this is possible now. That is all there, but we have the problem of delay. So to overcome delay, we are looking at a carry look ahead adder. So now in carry look ahead adder, what we look at is, see, now let me once again write the truth table. For you need not write, it is just to show. I'm only interested in the carry. Okay, I'm not writing the sum part because sum will be generated depending on the carry. So let me try to get the carry faster. So let's observe what happens to the carry. Okay. Now, if you observe the truth table, where all I have carry 1, these 4 cases. Now in the last 2 cases, see, when my A and B are 1, okay, irrespective of the value of my C in, my carry is going to be 1, right? Because, so I can say that C out is equal to 1 when A equal to 1 and B equal to 1. That is one case. Now there are 2 more cases I have to look at. So those, if I look at this one and this one, so I can see 0, 1, 1, 0. Okay, A and B are 0, 1 and 1, 0. And C in is 1 in both the cases. So 0, 1, 1, 0, I will get an output 1 when 0, 1. If A and B are 0, 1 or 1, 0, it is like XOR gate gives me an output when, if I look at XOR, yeah, 0, 1, my output will be for XOR 1. And 1, 0 also output will be 1. So if these two are given to an XOR gate, I will get the output 1 in that, only these two, okay. 1, why I will tell you. I will tell you why. 1 minute. So let's say, so that means that all other cases, this will be equal to 1 when A XOR B, and then I can AND it with C in. C in is 1, only in that case it works. Okay. Yes or no? Okay. So my C out is equal to AB or, okay, this case or, I'm saying, no, any one of these cases is true, my carry out is going to be 1. A XOR B, C in. This is a very similar expression. We already got this expression previously. It is our carry generated expression only. If you look, where did the carry go? Yeah, here. Okay, this is my carry. See, this is what I wrote now. Is it not? This expression that I wrote by simplifying whatever I had written from the previous thing. The same thing I'm getting. Okay. Okay. So this is the expression for carry. Okay. This expression is okay. How we derived this expression is okay, right? Now what I want to say is that, so if carry is equal to AB plus A XOR B, C in. Now this, if I say for the first carry, to generate carry C0, I can say this is A0 B0 plus A0 XOR B0, and that C in will be C minus 1, the first case. Right. Okay. So it will be minus 1. Now this A0, B0, A1, B1 and all are known to us because we are giving inputs to the circuit, right? A and B are the inputs that I want to add two numbers, so I'm giving those inputs. So inputs are readily available. Only problem I have is in the carry, right? So now I have written my carry expression in terms of, so this is something, this what I have a term for this, I call it generate. I can generate AB, right? If I know the input specific bits, I can generate AB. Okay. I can also generate A XOR B also. That is called propagate. Okay, because that has to be ANDed with the carry. So I call it propagate. Two terms we use. And so I can write C0 as G0 plus P0 C minus 1. I'm replacing AB by G. Okay, this is called G and P is AX or B. Okay, corresponding bit when I XOR it, I call it P0, and when I AND them, I call it G0. Okay, this way I generate it. So now, now C1 will be what? G1 plus P1. What will be C0? Right, the previous carry. Now C0, can I replace it with the C0 here? Yes, right. I can replace it with what the value of this C0 is, like an equation. Now let's look at the math. So G1 plus P1 and C0 is equal to G0 plus P0 C minus 1. Okay, I have replaced that C0 with this. So this becomes G1 plus P1 G0 plus P1 P0 C minus 1. Minus 1. Is there any doubt about how we got this? It's pure replacement. I made A and B as G. So corresponding bit I call it G0, G1, whatever. And A XOR B I call it as P, propagate. Okay. And correspondingly I name it as P0, P1 and so on. Now the first equation we know it is G0 plus P0 C. And this is what we have. So then in the next equation where I have C0, I replace it with C0 from the previous equation. Now what about C2? C2 will be G2 plus P2 C1. Yes or no? So I replace it. Please write what it comes to. Okay. Similarly, I can write C3 also. Okay, I'm writing C3 here. Okay. So now if you look at all these terms, you can write as many terms as you want. I can write up to C8, C9, C16, whatever. Now if you look at each of these terms, you can see that each term depends on what? Now C0 depends on C minus 1, which is the initial carry in. Okay. Then C2, C1 depends on, this is a term that also depends on C minus 1. Next one also depends on C minus 1 only. There is only one term which depends on C minus 1 in each of the equations, and that is C minus 1. It is not your so similarly CC3, if I look, that also depends only on C minus 1. That means I'm not depending on C1, C0, C2, and so on to get this. Okay. That means I have eliminated the dependence on the intermediate carries. Yes or no? You need to know how to write the equations, only then you know. Here we only have to generate AB and A XOR B. That is easy to generate because I'm giving inputs. My inputs are A and B. So whichever bit I want to add, correspondingly I can generate G0 and P0 or G1 and P1 and so on. And then after that, if I substitute in this equation for carry, I'm able to write everything in terms of the initial carry. That's C in what I have. So I'm able to eliminate the dependence on intermediate carries. Okay. Now we have to draw the circuit. See, now this circuit means each one, if you see each term here, okay, I have some plus plus plus. That means I have OR gate that is there. But before that, I have some kind of AND operations, right? So I have some AND gates, and all those AND outputs are all odd together. So that is what that extra logic that comes in. We will draw that, but I think I'll stop for today. Okay. Okay, next week also you have a similar extra class. We have already missed 2-3 sessions, and your portion for your first mid-semester exam would be up to what we cover next Friday. Okay, next Friday, not this Friday, next Friday.